Okay, let's have a class, and I have put all the slides on the eCampus, but after I prepared the class over the weekend and yesterday, I think I'm still going to using the chalkboard talk to talk about some important context here. The next week, if we have time, we're going to go over the slides, because every semester I do a little bit different of the teaching. So I will be still draw on the blackboard to talk about today's material. So we talk about the lipids, we talk about the fatty acids and the triglycerides, but there is a little bit other material which is chemicals belonging to lipids we haven't mentioned. We call it unsaponification. Unsaponification and saponification, and we also call these chemicals, we call it unsaponifiable. So when we talk about unsaponificables and the unsaponification, we first of all we want to talk about what is saponification. This means there is lipids, they can react with soap. So what is the structure of soap? Soap usually we could say it is a CH3, CH2, 14, COO, Na+. So you can understand it looks like a sodium alkoxy chains, or we can just say sodium fatty acids. It's just a nickname what I gave it to you for understand. And this chain, this CH2, that could be somewhere between 12 to 18. And they reacted with soap under heat and with alkaline solvents, or we say solutions, and they can react it. Now, in other words, there is some of the lipids, they cannot react with soap. Or we can say they cannot generate soap even. Reacted with soap or generate soap. However, we still call them lipids because they are soluble in organic solution and insoluble in water. So still fit the definition of what we talk about the lipids in water. Now the saponification, there is lots of examples. So for example, we had a stearic acid and palmitic acids. Those are the good examples. Now how are you understanding unsaponification? Very simple example. If you are processing some of the meat products, let's say the pork liver, afterwards then you go to use soap and hot water to wash your hands, and you find your hands is still sticky a little bit. Even you prepare like ground beef sometimes, you still feeling after you soap to wash hands is still sticky. That means there is some of the unsaponification, unsaponificables there. Okay, now what are they? This terminology seems like confusing, but if we give you some of the example, you will know very clearly. The number one is sterile. So what is a sterile? That is, we call it derivatives of steroids. And steroid, basically you can become a hormone later on. So what are the structures? Since we are in the chemistry class, we want to talk about structure. The structure is very unique. So what it looks like? You have a 6-carbon ring, another 6-carbon ring, and then you go here, you have another 6-carbon ring, and then you have a 5-carbon ring. That's the basic structure. It looks like it is A, B, C, D. So what's the structure looks like? It is 3 6-carbon rings with 1 5-carbon ring. And very unique, we had an OH there. And we had a hydroxy base there. Why it is important? Because this hydroxy base could reactive with to generate ester bond. It is the same thing. If you don't know about this, it is the same thing when you have a DNA. Remember when we talk about DNA, O right here, HCH2, this is the phosphates right here. This guy is connected, will have a diphosphorester bonds, and here is the same thing. When you have an OH hydroxy bonds, react to with generated ester bonds. When you have ester bonds generated, what happened? They will be increased surface activity. So we will talk later on about this one. Now what we want to mention here is that the label, how we going to label these rings. The label, we start from the top. This is 1, 2, 3. So hydroxy bonds, that's 3. And 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Now, there is some of the research has been done, and then do some of the chemical conclusion. And they find that the rings A and B, basically, they have methyl ends, or they have proton ends, both. And there could be trans configuration or cis configuration. Now, they also do some of the conclusions about CD ring. They find that the CD rings, they basically dominant with CH3, which is a methyl group, and most of the time the configuration is trans. So this is just give you a model of the stereo, what it looks like. So lots of you here, which is studied dietetics. So we want to give you a very simple example. Everybody knows it's called cholesterol. So what the cholesterol looks like? We know cholesterol is a precursor of bile acid. It's a precursor of vitamin D. And it is also a precursor of steroid. So this is steroid will become a hormone, which is have a, so let's say sexual hormone is belonging to that. So there is a joke we can always tell you that if the people have a strong sexual activity and a strong sexual emotional, they need to keep a certain level of the cholesterol in their body because those are contribute to steroids to generate from the physiology standpoints. But we're not going to talk about that. Since it's chemistry class, we want to talk about the chemistry. So what is the cholesterol looks like? It's very similar to that, but a little bit different. So we still have the rings right here. I need to draw a little bit lower. We still have the rings here, which is 6-carbon ring, another 6-carbon ring right here. So you have a 6-carbon ring right here, and then you have a 5 carbon ring like this. Okay, so same thing, we have OH, but what's the difference? We have some CH3 comes out, also have a CH3 comes out. So if we say, we draw like this, we draw like that, how are we going to label them? It will be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, but not done yet. Not done yet. I have to remove this. What happened is it's going to become out a little bit along here. Here's a C, then there is a CH3. Not done yet, so it's going to be 1, twist 2, twist 3, twist go here, the C, 8, C, then goes CH3 and CH3. That's what happened is cholesterol. So you can continue to label, that's 19, so that becomes 20, 21, 22, 23, 24, 25, 26, and 27. So that's a 27 carbon structure of the cholesterol. It's pretty magic. So we want to talk about something here is this guy. We already mentioned, we call this the beta configuration. Because they could react to generate ester bonds. Okay, and it's a precursor material for the vitamin D. So what that means? You all know we have a product called the 7' dehydrocholesterol. So what's going to happen? This will not naturally become vitamin D. Okay, when they become a vitamin D, they need some of the condition. One of the condition is UV light and irradiation. Now, you're not going to purpose to expose yourself to UV light and irradiation. Unless some people like to do the tanning, that's a different story. But what happened in our natural life? This will become sunshine. That's what we have to do. So, specifically in West Virginia, if you are October to April, okay, we'll say October to April, and also let's say May to September, what we have to do. May to September, it's a very good weather here. We have lots of national state park. Outside scene is really good. So we need to do exposure, sunshine, about 1 to 3 hours pretty much. How about October to the April? There's not enough sunshine. You need to oral take vitamin D. Now, vitamin D is very important for the bone formation and other immune system development, but you cannot take too much. There is more and more research showing the overdose of vitamin D also is toxication will cause. Number 4, we had a cholesterol. Cholesterol is highly related to a very bad lipids, is LDL, correlated to that. That is called a low density lipoprotein. So this is corresponding to cardiovascular disease. So what are they going to do? You have to try to avoid animal fat. So because animal fat is dominant with 2 components of fatty acids, 60. We mentioned these on and on stearic acids and palmitic acids. Okay? So what's the dose for that? The normal level? I believe it's about 100. Is that mole per dl? If it's that's a value for everybody, including diabetes and people who have a stroke or had a cardiovascular disease before. If you're normal people, you could be up to 130. Some of the labs, they are using the index, which is 130. Okay. In China, they're using a different level. They usually divided by 3. They multiply by 0.03. So normal people should be, it should be 0.026. So normal people, it should be below 2.6. And when people have diabetes or have a cardiovascular disease before, they should be below 2.6. And the normal people should be below 3.1 or 3.2. So that's something I just want to briefly mention here. So this is a cholesterol we talked about. And the second thing, also belonging to the unsaponifiable, which is a wax. So what is wax? Everybody heard about that in your life. The wax, it is a long chain, which is a very long chain. Fatty acids and with long chain alcohol. So what it looks like, the chemical structure, it looks like very, very long. Then go here, CO, go here, O, and then go here. Very, very long. So just to give you an example, if it's a bee wax, what it looks like, CH3, CH2, 24, carbonyl group O, and then you have CH2, that will be 29, and then go CH3. So that's the structure. So this is also, we call it a wax ester. Now, what is important for the wax? There are basically 3 different types of the wax. One of them called mineral wax. We didn't mention this, not recognize this too often. But we know there is an animal wax. Let's say you have a pheasant. That's an animal wax. And we also had a plant wax. Plant wax widely existing is on apples. Apple had a natural wax, and in some of the country, they also spray with the wax because they want to do is dehydration. The dehydration have 2 reasons. One of them is to repel insects and also the worms and all other things. But I did the research before with my first postdoc in 2020. We're using a different extra apicular material from the leafy. Some of them have a higher wax, some of them have a lower wax, and we find that the wax could decrease survival of salmonella, so decrease the survival of bacteria on the surface. And we also did the research with Rebecca and Connor using different apples to see the bacteria survive there. And we do find that Fuji apple, which is the survival of the pathogen, is, especially Listeria, is dramatically lower compared to the Honey Crispy apple. And we did not testing the waxy amount Because the waxy amount you have to using GCMS have a lots of the standards to do, because there is alcohol, there is ester, there is a fatty acids, 5 different components. Since as a postdoc left here, we lose the standards, so we cannot do the measurements. Otherwise, we will do the measurements for the different wax amount and the different type to see the bacteria survive. There is a tons of research doing right now by University of California, Davis. They are worked with Centers for Produce Safety. They are talking about manually spray the wax on the plant surfaces. Then they try to see the bacteria survive, and they try to do the modeling about that. So this is about wax. Okay, the next one is phospholipids. Phospholipids. This is we talked about before. You more or less know some. So what is the general structure of phospholipids? So we same thing, triglycerols, H, goes H here, and H. So you have this sterol specific number 1, sterol specific number 2, and right here it's a little bit special, but you already know it is a phosphate, okay? A different type of the phospholipids really depends on the X. So the easiest one, if this is OH, hydroxybonds, we call it a phosphatidic acids. Very simple. If this X is O, CH2, CH2, NH2, let me just make sure, NH2, we call it phosphatidic tidal S-nolamine. If this X is OCH2, CH2, M plus, and CH3, this is a very important one. Phosphatidyl-chlorine. What is that one called? This is choline, sorry. CHOLINE. This is we call lecithin. Why it is important? It is a natural plant emulsifier. It's widely existing. More than 50% of the time, they exist in the soybean. We'll talk about this emulsifier real quick. Okay. This is also, we have a nickname. We call it a plant HDL. So that is important for the phospholipids. We gave you some of the examples. Now phospholipids, Ian, could you just move it right here? Yes. Don't turn the angle. Just make sure. Turn around a little bit. Yes. Turn around a little bit. Yes. That's good. And the phospholipids, we also want to say there are 2 different types. Okay, they are could be linear. We already know linear. We learned in your biology class. We mentioned a couple of times is a fluid mosaic model. Okay, you have the protein and the phospholipids. So basically, you have a hydrophilic and a hydrophobic part, which is head and also tail. Okay, this is, we already know about that. This could be linear, but in the food products, especially in the milk, it is could be circular. So circular, what it looks like? It looks like this. and then like that. And then it becomes this way. That is very important. Works like this. The phospholipids have a very beautiful circle there. This is, I just draw a couple. What do we call it? Micelle. Why it is important? Because it's the same thing as an emulsifier. And it should be important in a aqueous status. Now, which products have a huge amount of the phospholipids, which is circular? It's milk. Now, which products is that? Casein. And I mentioned about this micelle is an emulsifier. That is why the milk could be worked very well with water, with lipopolysaccharide, with phospholipids, with fatty acids, and also with sugar, with other things, because the milk casein is like a micelle, is like an emulsifier. They are connected with them, reduce the surface tension. Okay, so this is why we talk about phospholipids. I'll give you some of the examples. Since we mentioned about the emulsifier, so we're going to spending some time to talk about the emulsification today. Okay? So we're going to talk about number 4, which is emulsion and also emulsifier. Okay, we mentioned about a little bit the egg mayonnaise, but we haven't go detail, so we want to go detail talk about that. First of all, what means emulsion? Emulsion, which means heterogeneous system, and their system have a different ingredients there. Basically, it's oil and water. That's a major components. But it is a highly unstable, or we say with very limited stability. So what it looks like? Just give you an example. I had a water. This is water. Then in the water, we have a kind of like a fume or system. Then we have some droplets. So that is the oil droplet. Now at this moment, what do we find? The water is a continuous phase. And the droplet, it is dispersed there. Here and there, everywhere, so we call it a disperse phase. So, this is kind of thing mixed together, but without the emulsifier, looks like a highly unstable. Let's say egg mayonnaise looks like that, but why egg mayonnaise not looking too bad? Because there is an emulsifier there, okay? So, this is an example. Now, this comes out with one of the model, which is OW model. What is OW means? Oil disperse phase, or we say uncontinuous phase, and water is continuous phase. Now, what type of the product is OW type? Is OW emulsion? We know about egg mayonnaise. It could be cream, it could be dressing. So you're feeling about that. If you have a dressing, you see the Majority of them are water, they're a little bit sticky, and then you find that there's oils there. But they also have another situation happened, which is WO. So you know what we're going to talk? That means oil is continuous phase, and at this moment the water is a dispersed phase. So what is the product looks like this? We know that your butter looks like that. So let's say cocoa butter, and the margarine looks like that. Margarine looks like that, and the shortenings looks like that. And it's very important. The water is there, the oil is also there. But when determining the food quality, the oil is more important. So for example, if it is oil and water phase, oil is dispersed phase, at this moment, this oil will be determining viscosity. Viscosity. But how about here? The oil is a continuous phase. So when you buy a butter, what do you care about? How tough it is that right? So we're going to talk about here. So water is determining firmness. Okay, so that's all the two phases we talked about. Now, and we also gave an example. Now, we want to talk about these emulsifiers. So we move to this section. We talk about second one is the emulsifier. So we talk about this emulsion. It is a very highly unstable system. The stability is limited, and we want to add some of the surface activate agent. Could connect it with it. Not really connected, it's a quotation mark connected with it. Now how they do, obviously, they're going to low down, lowering, or we say decrease surface tension. So how they do it then, the question is. The research has been done back in 1950s to 1960s, or by the chemistry, or for the chemists, and the chemists, the physics persons, they do. So they find that the curve, what it looks like, the surface tension, we using a physical index which called dynes. Okay, so the y-axis is dynes, and this means surface tension. So I have like 10, 20, 30, 40, and 50. Okay, so I'm going to draw it a little bit clear. This is 50, 40, 30, 20, and 10. What's the x-axis means? This is a concentration. This is the concentration of the emulsifier. So the concentration could be 0.1, 0.2, then we go 0.4, 0.6, 0.8, and 1.0. Now what it looks like, it's very interesting. The curve looks like this, and the curve also looks like that. And actually, if you want to draw it more clear, I'm going to break this down. It looks like this. So what this tells you? This tells you it does not mean you using higher concentration of the emulsifier will cause, in fact, what you desired, what you want. It's very interesting. Let's say the initial somewhere is 40 to 50 dynes, and I want to reduce to 10 to 20 dynes, so I actually should use a concentration is in this range. So they have a conclusion, which is they talk about if you're using 0.1 to 0.2%, or basically say less than 0.2%, you could decrease the surface tension from 50 to 10 dynes per centimeter. So it really depends what we should do, okay? So that just tells you that reduce the surface tension, but does not mean the concentration, the higher the better. Basically, we should be using 0.1 to 0.2. Now, then have another question for you. How are we going to choose an emulsifier? There is a lot of the emulsifiers there. The one what you heard about is span. I believe you heard about span. And in your chemistry class, twin, those are the things you heard about. So, and there's other commercial names for those emulsifiers. So how we determine that? Then there is a formula to determine which is HLB system. So what is HLB system? H, hydrophile. L, lipophile. What is B? Balance. So that is called the hydrophile, lipophile balance value. And this is a formula. And what is the formula for? It is 1 minus 20 multiplied by S divided by VA. What is this S means? That is, you need to go back to look at that. That is a saponification value of fatty acids ester bound. Now, of course, this fatty acids is in the triglycerides. What the VA means? That means the acid value of fatty acids. We call it a radical. So this gives you this formula. Now, what type of the results we will get? The results we will get, the HLB value, there is a range. The range is 0 to 20. So we go back to here. It's really depends. It is OW or WO situation. If it's an OW situation, then the value has to be in the middle. So we call it a intermediate HLB value we could be using. Okay? Therefore, we should be using somehow like span 65, somehow like span, not 65, span 20, 40, 60, 80. Span 20, 40, 60, 80, because their HLB value is around 4.3 to 8.9, relatively in the middle. And we also could use a twin. So we have a twin, 61, 81, they will be 8.6 to 9.6. That's HLB value right in the middle. The reason is that, we'll talk real quick. The reason is, once you use this emulsifier, we want to keep, let's say the egg mayonnaise, we want to keep this beta prime polymorphism. And we don't want them to become beta, because when you become beta, the egg mayonnaise is no longer egg mayonnaise. It's going to become very tough. We call it a grainy. Okay, so if it's a beta form, it will become grainy. That is what chocolate looks like a little bit. So, but how about here? If it's WO status, what we need to choose the HLB value is much lower. So we need to choose a lower HLB. So what do we have? Span 85. That's only give you HLB value equals 1.8. But then you have a question, if I have a very high HLB value product, so what are we going to do? If HLB to 16 to 20, this is a solubilization agent. So actually it helps to solubilize most of the products. It's no longer be helping like emulsifier, okay? So this is something we want to mention about the emulsion and the emulsification. Now, what are the examples of the emulsifier? We mentioned about mono, diglycerides. And we just mentioned about leucine is a natural emulsifier that is used widely. So if you want to draw the whole thing, R1, you go here, H, CHO, R2, and then go here, HO, go phosphate. Then go here will be CH2, O, CH2, CH2, so you go N plus and CH3. That's the structure, what it looks like. Okay. Okay. Since we already talked about this guy, so we want to talk about the polymorphism of the lipids. So that gives you another big topic right here. Okay, so let's talk about polymorphism of lipids. Ian already mentioned about in his slides a little bit, so yes, thank you. Now we will talk some more here. What happens for the polymorphism? We need to talk about from the beginning what happened. Lipids, we know, we can say it is the transition between solid to liquid. And most of the time, we also call it a plastic solid, or we say semi-solid. So what happened? Solid to liquid is very simple. Think about if you have left chicken soup and mixed with a drumstick, let's say. Okay, you try to make a noodle. And it's very sticky. And then you said, I'm going to do an easy way. I put it in the microwave to heat it about 45 seconds to 1 minute. They're all melted. And it's no longer sticky, it becomes a liquid. So solid go liquid. We need heat. And the volume will be increased. That is goes that way. However, liquids go to solid is not completely reversible. That is happens in the food chemistry all the time. This will be release heat and the volume will be decreased. Now at the same time, they will generate crystallization, which means they will generate a crystal. And crystals, that is a lipids crystal. Now, in the real life, the food products have a different components of triglycerides and different composed by different fatty acids, so their melting points is different. So therefore, some of them will have a crystallization, some of them will not have a crystallization. And some of them is interacted on in the middle, therefore, they will generate a different morphology. This means a shape, you can easily think about it, is a shape of lipids. Now what are they? What are they looks like? There is a different system. We will talk about the easiest system. There is 3 different morphology. Always it's a polymorphology, which is alpha, beta prime, and beta. Some of the other textbook, they say there is a gamma, there is a beta prime, and there is a beta 1 and beta 2. But we don't talk about these. It's too complicated. Okay, we just speak briefly. Now, what do the logs like? The way what they do, they draw, they using a X diffraction image. So they draw three lower 1, lower 2, and lower 3. And then they cut it cross section. So what you're gonna see it. Alpha form, what it looks like, is we say it's red. So what looks like? This like this, right in the middle, this like that. This could be like this, like that, right in the middle, like this, like this. Their number, their morphology are not in order. So we say this is a disorganized hexagonal zigzag stacks. And they also measure the distance between the different layers, and they find the distance is about 0.42 nanometer. So pretty large space. It's an unstable status. Now the second one we want to talk about is the beta prime. Then we talk about beta. Now what is the beta prime looks like? The beta prime, it looks like you go this way, go this way, go this way, and then you have couple like that, couple like that, couple like this, and then like this, like that, and then like that. So what it looks like, it is perpendicular. And they think this angle should be 90 degrees. Not really. Some